my talk basically is about faults. And I promise that it's everything about a fault with a disclaimer that it's not actually everything, because we're going to spend too much time on that. But yeah, I've been working with Scala since a lot of time. I think it started in 2008. And I really got fascinated by the functional side. So I started to try to learn a lot of that. So I banged my head against the wall, trying to understand complex stuff. Sometimes I had success, sometimes I fail. But I like to try to tell everybody about what are the problems I had and what I discovered on the way. So basically, this talk is you could have invented faults, right? Do you use faults? Basically, do you program Scala? Yeah, cool. I like it, so it's good. Do you use faults? What usually do you fault on most of the times? List, yeah. I mean, that's kind of where the problem starts, but it's amazing. I mean, I started with learning Scala, learning about folding on the list, and it's amazing. You have a whole list of things, you put a couple of functions, fold, and you get a result. You don't need to iterate, check index, whatever. It's just very easy. But then you have to remember for right, for left, which one is stack safe, which one doesn't work. And then I started learning more stuff, and this kind of a fault is not that just an interesting function to use. They have some kind of background that understanding that allows you to get a better understanding of how fault works and why it can be useful in other places. But let's try to reinvent the wheel so we can learn something on the way. Basically, very simple problem, how to sum all the elements of a list. You have a list of numbers. You want to write this function, right? How you will implement that? Yesterday, somebody told me, OK, you put nums.sum. Yeah, but that worked, obviously. We are not going into that. The idea is, because we are trying to build from functional programming principles, we're going to use recursion and pattern matching as the basic tools. This is an amazing book. I really like it, love it when I did it. The Little Schemer. That covers a lot of ground in like this, 100 pages. It takes you in a tour for the whole computer science thing. But you start building all your programs in Scheme using recursion and pattern matching. And we are going to try to use that. So list in Scala, this is how we declare list. But basically, we are building. You remember what are the components of the list? Yeah, it's kind of you have a head. I mean, there's the colon that you put together an element and a list, and it's the empty list that is new. So you want to use recursion and pattern matching. We did a case for those two options, right? So if you want to get the sum of the list, what we put in the first line?
0.
Exactly. That's good. Yeah, 0. And in the second line?
X plus some x's.
Yeah, exactly. The first value plus the recursive call of sum. That's a good one. Yeah, you made it. OK, that's a good one. This kind of using only basic functional programming things, pattern matching, recursion. OK, let's try the same exercise again, but with strings. We want to convert the list to just a long string, right? Again, what we use we use the same thing. We use pattern matching. We know that at least have the nil case and the cons. Actually, in Scala, we have this. Normally, that is known as the cons list, the list you prepend elements before. So we have the case of the head and the tails. What we would do the first case? Empty string. And the second case? Kind of, yeah. We are going to abuse just a little of Scala. We use like this. Basically, we concatenate the two strings. One thing I would like to have done is to be more explicit. It should be x dot to string, just to be sure, because int is not a string. So, but yeah, we're going to let Scala convert that to string automatically. So again, we got the empty case, which is the empty string, and the case with the head and the tails is the head converted to a string concatenated with the recursive call. That's good. We have two codes that looks pretty much the same. We're going to try once again the same list, but right now we're going to do a little more complex. We're going to use generics. We want to check a Boolean property. We want to check that the whole list complies with fulfills the property. So again, we use pattern matching. What we'll use in the first case? True, yeah. Somebody yesterday said false. And it was interesting, but it wouldn't really work. But it's interesting. Yeah, basically you can prove anything for the empty list, right? So now, more interesting for the second case, when you have the head and the tails. Again, so where we had to put the recursive call because we are already doing the recursive in all the other places. So what you will put here? Sorry. Yeah, we use true for the empty case, and in the head tails case we use the element we have in the head matches the property, and the rest of the list matches the property. So to summarize how we did recursion, we have one definition for the empty case and one definition for the head and tails case. And if you remember how what is called the const list, that immutable list in Scala works, that's kind of, we are doing recursion in the structure of the list. The empty list is our base case in the recursion, and we have the head and tail case where we do something with the head, and we recurse on the tail. That is important because one problem with general recursion is it's not guaranteed to terminate, right? If you just do a recursive call, you don't really know if you're going to terminate or not. But if you know, and even if you're more formal, you can prove that you're doing structural recursion, you know that your program will terminate. That's kind of an important thing, because otherwise we blow stack and stuff. Sorry. But we have these three pieces of code that look similar. I mean, they do different stuff, but they look pretty similar, right? So, I mean, once is okay, twice, okay, but thrice, I want to refactor and make it more general. So here there are three functions, and I put colors to make it more evident what we are doing, right? We have in green the empty case, the case for the empty list. In the case with the head and tails, we do something with the head, and we combine it. The blue is the combination with the result of the recursive call that I put in maroon something. And because this is Scala, we can abstract that. We can pass functions around. And we can make this code more generic. Basically, we need one value for the empty case and one function that combines the value with the recursive call, right? yeah, I just put whatever I just say in the slide. So this is kind of my proposal for the recursion over list. You have a value for the empty case that we use here, and a function that takes an A of the list of A's, a value B that will be the result of the recursive call, and yeah, the list, and returns a B. And right Z is the value for the empty list, and basically we have a function that takes an element and the result of the recursive call, and I'm missing a parenthesis here. Do you agree with this? Okay. Except the location of the list parameter. This function, this signature, did reminds you something? Exactly. All right. So we're kind of derived our own fall right. You know, the original version of this talk was in Haskell. I'm not an expert on Haskell, obviously, but I write everything, and then I write this code, the equivalent of this code in Haskell, and I went to the standard library of Haskell and looked at the definition of fall, and it was exactly like that. So it's kind of it was just a step of just a generalization of some of the steps, getting something generic of that, and basically we have fall. There is one little detail, but yeah, sadly, how we write it, and basically fall right is not that recursive, because you have to apply a function after doing the recursive call. You have to get the result first, so you cannot really do take-all optimization of that. And you have to be proved wrong on that. Well, yeah, usually, so if you informally define fall, I don't know, one of the things that came to my head is like giving a function that combines an element with accumulation and an initial value, start with the initial value, traverse the list backwards because we're going fall right from the right, apply the function to produce a single result. Do you agree with that explanation of fault? It's kind of, I tried to create some explanation that, based on what I know at the time, the kind of important thing is like the result is basically this. You have a list of A1, A2, N, and the result of the fall is basically putting all this together. But yeah, again, this is not that recursive. So far, so good. We create our own right-fall for lists. But what about other data types? We are really used to for right or for left for lists. Does it make sense to fold other types? We're going to do it, and we're going to start doing the same kind of exercise we did for lists. But let's try, we have a binary tree. I just make up a binary tree. We have a branch that takes two trees and create a new tree, and the leaf that holds a value. And we're going to derive our own fold for that type. Also, let's see about what happened with that either option. There are not lists. There are not even recursive data types that grow. There's like a fixed number of elements. But still, we still can fold that. And basically, by repeating the same thing we do, we're going to figure out how to. Let's try to do the same exercise. Let's get the sum of all the elements of a tree. If we do the same as we did for list, what we put here. We do pattern match, and list we do pattern match on the empty list and the cons. Here, what do we have? Yeah, basically our data type has only two constructors. We have the branch and the leaf. So we're going to pattern match. Our B tree can be either a branch or a leaf. We're going to pattern match on that. So we have our case for the leaf with an element, and the case for a branch with the left tree and the right tree. If we want to get the sum, let's say the simple case, what we put on the leaf.
Number in the leaf.
Yeah, exactly. Basically, if you know that the tree has integers, this a is an integer, we can just return that. In the case of the list, we didn't have any value, so we just return 0. A little more interesting, what we put in the branch. Yeah, we do a recursive call on the left branch, and we do a recursive call in the right branch, and basically we sum together those two results. Yeah, that's how we get the sum of the tree. We're not going to do it for the properties, but let's try the same thing with the toString. Again, we do pattern matching with the branch and the leaf. What we put in the leaf? This a toString, because even this one we're using generics, which we have in. And here we put the recursive call of the string of the left side concatenated with the recursive call of string on the right side. Cool. Yeah, that will allow us to give us a tree and return a whole string concatenating everything. So if we do the same exercise, we take those two functions, sum of the tree and the string of the tree, we generalize it, and basically we need a function that takes two results of recursive calls and combine it into one. We need a function that takes a value from the tree and returns one value. That converts basically the value in the tree into something we want to use. Do you agree with this generalization? Like it? You want to improve it? I don't know. I just write it based on what we already have. I try to refactor, generalize, and get this. But now it gets interesting, right? Let's compare the two things together. And we try to get to what is really a fold. So we have the list that it basically is const of a head and the rest of the list. Basically prepends an element into a list. And we cast the case of the empty list. Actually, if you go to Scala, it's object nothing. But just for the sake of making things a little more consistent, let me use nil a. So this is basically our type constructors. And our recursion, our fold, takes a function that takes an element and a result and returns a result. And also we have a function value for the empty case, the result from the empty case. And then with those two functions, we fold the list and get a B, a final result. And the interesting thing is, if you take the initial list, that is 1, 2, 3, if you use this list, in the Scala list is the same, but this is kind of easier to write. We have the const 1, const 2, const 3, and the empty. And if we apply the fold, we get this, f of 1 and f of 2 and f of 3 and z. There is some kind of similar structure there, right? And if we go to trees, we see something similar. Our tree was either a branch of two trees or a leaf with a value. And the recursion or fault recursion over the tree was something that combines two results into one result or takes a value from a leaf and returns a result. So again, if we have our tree written like this, like a branch, branch, leaf, leaf, and leaf, and we fold it over it, we get f of g of 1 and g on 2 and g on 3. And then there is again a similarity of the data type and how the functions get applied. So that's basically what fold does. Replace data type constructors. If you think of the data type constructors as functions, fold replace that with the functions you give. That's why here, in the case of the tree, you have an f and g, and you replace branch with f and leaf with g. In the list, you replace const with an f and nil with a z. We're going to see more things, but that's kind of the most important point of the talk. Fold really, what you get with folding is replacing the data constructors with the functions you provide. And that's really how it works and how you would think for different types. So since we are here, and now that you know what we are doing, I want somebody who going to tell me the signature of the fold of option. We have basically two cases. One of known that doesn't have any input value. So here is a very similar case as the list, right? And here we just need a function that takes one value, converts to a result. So here known will get a b, and sum will get an a, and we need a function that from an a gives you a b. And we can do the same here. If you think this as functions, here we need like a new letter. Suppose the result is r, the type of the result is r. And basically, you have a constructor that basically takes one type, a type of A, and you return basically, if you think of constructors as functions, here you have a function that takes an A and returns a left of AB, and here you have a function that takes a B and returns a right of AB. And the way we were doing folds based on the constructors, we need to replace this with a function that takes an A and give us a result. And here we need to replace right with a function that takes a B and returns a result. That's how the kind of type replacement works. And based on what we saw, this is what I wrote, right? In the case of option, we have a value of type B for the case known, and a function that takes an A and returns a B for the case of sum, and all that, the whole thing returns a B. And same thing for fold on either. We have takes ABC, and we have a function that takes an A, returns a C for the left case, and a function that takes a B and returns a C for the right case, and everything returns a C. Sorry. So basically, we wrote this based on what we saw and what we were trying to do. And actually, after writing this, I went to the Scala documentation. And basically, if you see, this is the signatures of fault on option and the fault on either. Here, if you see here, this is missing the actual option you want to convert because it's actually here in the dot. You put your value dot fault, and you give these two functions. Same here. So we kind of we derive based on what we were doing. We derive the signatures, and it gives you things that were already there. We're kind of the right track. Sorry. So finally, after all this, what is really a fault? Why is called a fault? Fault really transforms the input into something else following the structure of the data type, because all the functions we give follow the kind of the inputs and outputs of the data type we create. And you will see it mentioned in the technical literature as catamorphisms. Catamorphisms are the generalization of a fault. That comes basically, the word kata means downward or according to. Basically, it's a collapse. You have a whole structure and you collapse into a single value. And it's kind of a joke. There is a marvelous explanation in category theory for all this, but this is like this narrow to contain, so I'm not going to do it. But we are going to see a little. I'm going to try to explain because, in my case, I think I don't even get the total explanation, but I will see. I will show just a little. How are you doing so far? Questions, complaints, tomatoes, or something? Cool. 1 second. Yeah, this slide is just here as a kind of not really a joke, but this it's kind of get hairy, weird, and I try to explain, but basically catamorphisms are the generalization of the fault in functional programming. Catamorphism deconstructs the data structure with an F algebra with this underlying functor. What the hell that means. Okay, this is a generalization of a fault. The deconstructed part, we get it because we have all the pieces and we collapse it to one value. But then now comes the weird stuff, the F algebra. You know, there's a tricky thing. You start reading stuff, or especially in Haskell and whatever, people keep saying algebras. And I don't know, does anybody have a good explanation for an algebra? Yeah, I tried to get something good. I couldn't really find it, basically because everything, I think it comes from abstract mathematics and everything. But when they talk about algebra is when you have a combination of stuff, you have rules to combine things, right? And here, or if you are talking about recursive types or constructors, tell us the rules of how to build stuff. Basically, you're saying if you want to create list, you either have an empty list or you combine a value with another list. If you have a tree, you either have a leaf or you have two trees, and I tell you how to combine. That's what I call the algebra of constructors, because basically you have different ways of combining stuff to create new stuff. Stuff with stuff with stuff. Yeah. And then underlying functor. Do you know what is functor? Functor is mentioned a lot because it's basically one of the basic stuff of category theory. But in programming, In programming language just means something with the map function. In category theory means something that allows you to move from one category to another. But in programming, we are not moving from one category to another. We are talking about code. What happens is, then comes another word, strange word, that is end of functor. Every time some functional programming talks about a functor, it's actually saying end of functor. It's trying to trick you into thinking that it's talking about generic functors, but it's no. They're end of functors. That means functors that move from one category to the same category, because we're still talking about code. And basically, what it really means, a functor is a data type constructor. Because even if you have a data type constructor, you're creating new objects, you can really derive a map for that. So that's why. But this is all category theory. That's why they say functors. And basically, because a functor has map, and to have a map, it needs a parameter, right? We have the list. The list has a generic. Basically, if you look into Scala, anything that has a type parameter, a generic as Java, is an end of functor and can have a map function. And because we are using type constructors, we have the underlying functor. That's a lot of weird stuff. And the way those category theorists have to say about fault is like, okay, you have a functor that creates a type. Basically, this is the tree constructor that takes two trees and returns a new tree, or the function that the constructor that takes a list with a value and returns a new list, right? And this is the other case. I think when you're working on the list and you take the result of operating into list and returns a new result, or combining the two elements, the two results of working on the tree, and return a final result of the combination. There's I haven't seen it really. I had to be honest. But the whole point of that is like this arrow, this combination of arrows are unique. So for every data type, there is one fault that is unique. There's a unique fault. There's only one way to replace that. Here it mentions in F. In F is called the initial algebra. Okay, we go to that. Initial algebra is, in this case, is the algebra that creates all the data types, right? We have, basically, again, it's a very complicated way and formal way to say that's how you describe your data types. We describe the tree as, okay, you get two trees, put it together, and get another tree. Or we have one value, and put that with a leaf, and you get a tree again. That's the initial algebra. And then what he's saying is the fault is the unique way to go from that initial algebra and any other algebra, replacing the constructors with the functions in the algebra. And finally, that means that fault corresponds to the definitions of recursion, of structural recursion over the type. But going here, basically what we are saying that fault is the unique way to go from here to here. That's a whole theoretical explanation of saying there is only one way to go from here to here. Here again, this will be the initial algebra because it's a combination of type constructors. This is another algebra because it's a combination of other functions. Do you guys get lost? I don't blame you. I almost get lost. Okay, this is kind of a stepping point. This is a way to basically make these things a little less scary because there's a lot of very interesting results from this. Because obviously, those category theorists are not happy with only one level of abstraction. So there is a way. You have the initial algebra that describes how you create the data types. But then also you can generalize over that. Sorry. You have different algebra. As we see here, every data type constructor defines an algebra. But also, if you abstract over that, you have one initial algebra that generates other type algebras. That's kind of too much for me. But since you know how to fold algebras, and you know they are unique, you have this algebra that abstract over any type, and you know how to fold that. And the result, that means like you have only one fold for any kind of data type. With only one piece of code, you can fold over lists, over trees, over any other thing you can describe in an algebra. And that's actually what is called recursion schemes. If you go, there's a library now called Matryoshka that uses all the kind of stuff to create generic code. It's interesting. I mean, right now I don't know how it really, how much practical it is, but it's really interesting because it's with only one piece of code, you are kind of really ready to tackle any kind of data types. I mean, there's just one way to, I don't know, to transform like you're doing false. But if you want to get I don't know, yeah, the sum of all elements of a data type, you can have a sum that works either with trees, with lists. You can have a serializing code that it doesn't depend on the type you're passing, it just works on any type. You don't need to write again serialization code if you add a new data type, if you add a new type of customer, whatever. You don't need to write new serialization code. And that's kind of an interesting promise. But yeah, this is just joking around with category theory. Actually, there's a paper that describes a lot of stuff that is mentioned. It's called, this was one of the funniest names I heard. It's called Functional Programming with the Lenses, Bananas, Envelopes, and Barbed Wire. I tried to read that paper. I couldn't get anything until I started learning category theory and other stuff. I took a course about generic programming, and that's where it doesn't make any sense to me yet, but at least I can understand what they are talking about. So I mean, it's not critical, but it's an interesting thing to know where things could go with interesting results combined with practical libraries. We can get way better code than we do now. Obviously, we write excellent code. Everybody does it, right? But I mean, there are even more interesting things to do. So next party, when somebody asks you about faults, you can say, after all, a fault is originated by the unique homomorphism that exists between the initial algebra and any other algebra. That's the problem. I can guarantee that you will be the star of the party with that. Well, it's like it has some disclaimers, but anyway. Okay. So far, so good? Don't worry about the category theory. It's mostly as a joke in the talk. But yeah, there's a couple of things interesting. This kind of are interesting to try using the repo. I don't have it right now, but we can do it mentally. Or if you have a computer, you can do it. Okay, you have the list, 1, 2, 3. what happens if we fold passing nil and basically the cons operator? Yeah.
Just a copy of the list?
Yeah. I mean, you can see it even if you remember when you had you replace cons with f and z, the nil with z, and basically you replace nil with nil and cons with cons. You get the same list. That's kind of useful. I don't know. But based on that, let's do an extra step. We got this function that I call ffffff that takes a list, folds over the list, gives for the nil case, it gives nils again. But when I get to the cons case, I have the head, I have the tails. But when I'm combining, I put f of x. I'm combining with the rest. Yeah, that's actually, this function is mapped. If you try with this, multiply by 2, the result is you get the first element, multiply by 2, the second element, multiply by 2, and the third element, multiply by 2. That means once you have fold right, you can do a lot of operations based on that. I mean, you can create map, flat map. I think, I don't remember exactly, but even in functional programming in Scala, the book, one of the exercises is derive a lot of the normal collection functions using only fold right. Because fold is basically one of the fundamental operations over lists, over data structures. Yeah, that's kind of the point of the talk. Usually you won't get focusing on fold is for list. Fold is a lot more than just list. Yeah, if you ask category theorists about this, they'll tell you, oh yeah, fold is a combination of, map is a combination of a catamorphism with a type functor. And once you get that, try to digest that. Basically means the type functor is the functor that creates the list, the functor that creates your type. So basically, it's a function applying into the constructors. But yeah, it's so yeah, that's what I had to say. Thank you for being here. If you have questions, complaints, I usually ramble about many things in Twitter, or if you have questions, send it. You can send it to an email. Yeah, feel free to ask questions, complain, or whatever. Thank you. Questions? Or yeah.
Yeah, can you just go back to the algebra slide real quick?
You'll have to repeat the question for the recording.
Yeah.
All right, great. So I just want to make sure we're on the same page here, right? So I get, all right. So we have our initial algebra, we have some other algebra, and then we have each of them has their constructors. So this fold here is on the bottom. That's so given the functor. What does this f fold fh here on top mean actually?
What this means? Yeah.
Yeah.
This kind of is the transformation of this algebra into this algebra, and that is kind of a little not easy to visualize. I could double check the details, but if you follow this, basically this means this is kind of the algebra of folds. It's really weird, and it's a transformation between this functor of types into another functor of results. Actually, this part is not really used practically because a fold is just a combination of these. That's kind of that's why it's weird. I mean, you need in category theory, everything is based on make the diagrams commute means basically you have usually looking for this square and this direction of the arrows. So you can say this part is equivalent to this part, and this part is how you. This part is kind of the equivalent of how you do it with recursion, and this part is how we do it with the fold. That's why. But yeah, don't get hung up on that. But I wanted to look at the details of that because.
Okay, right. So in the bottom, the homomorphism here is just along the types, and on top it's over the functors directly.
Yeah.
So you can do it. I guess you can do it in either order.
Yeah. I think the point is this part is. It's more difficult to generalize, and you can write like a generic code for that. That's why you have one fold function. But yeah, I mean, at some point it's even harder for me. I promise I can check the material from I get that and get back the exact answer for that. But right now it's kind of I forgot about that. Yeah.
I'm wondering about fold left. So you focus on fold right because it fits this pattern of replacing the type constructors with functions. So is there a way to understand or to fit fold left into this way of thinking?
Exactly, and yeah, I forgot that, and it's a very interesting question. I don't have anything to type, but do you remember the signature of fold left? There is one thing. Basically, the main question is what happened with fold left, because we are saying folds fold match the shape of the constructors, replacing constructors with functions. But fold left, it looks like it works on lists. We have the empty case, but the function is kind of backwards. And basically, also we should say that there's only one fold for each other type. And we're saying no, but the list has two. And there is an interesting explanation for that. They have a.
Would you like a whiteboard?
Yeah, or I can use. Anyway, I can type something in there. Because this is a really interesting problem. Let's go backwards, right? Let's find out the signature of fold left, and let's figure out what that means. Oh, yeah.
Oh, we should probably not have the projector on it.
Yeah, that's
Move it over there.
cool. Okay. Yeah. Fold left. Fold left. Does anybody remember the signature of this?
Just like the right of the accumulator and the F
Yeah. Let's assume, let me write it in the generic way. We have A of the elements of the list, and B. We have an empty case, type B. And now the difference is here, right? You have the F with, that is a function. In for right, we have a function AB to B, right? But in for left, we have a function B and A to B, right? So far, so good? Cool. I'll say, okay, so if we already said that for replace constructors with functions. So what will be the constructors of this list? We have this one. This one is easy. It's the same as the other list. It's nil. Not the same nil, but something for the empty list. The same. I don't know. This something to say that it's not the same nil. Let's say nil 1. And what will be the other constructor? We have in the other list we have cons that takes an A and a list, right? And this is kind of what matches that. Here our constructor, how it will look like? Yeah, something that takes a list and an A and returns a new list. Okay. Oh, my writing is horrible. But if you see, it's something that takes an empty list or some list and start adding elements at the end. It's kind of the normal list is the cons list, and it's a prepend list, the functional, the most kind of popular list using functional programming. But this one is kind of a list, but goes to the opposite side. Goes with a pen at the end, and that's kind of weird. And actually, I look at after reading all this, I did this same exercise and say, but that list exists, whatever. I type it, and it turns out this one is called a snock list. Basically, because it's the reverse of cons. And it existed, and it was something like that. And it was kind of a reinforcing way of we are kind of the right track. Basically, based on we did the reverse way. We know that for replace constructors, so we figure out how the constructors will be, and we found out that it's something that really has already been invented. Obviously, what happened is really, if you have list 1, 2, 3, is really equivalent to either cons or snock. It's still a list of elements that maintains the sequence, but really it's just a matter of like order of execution of some operations. So basically, you can say that the two lists are isomorphic. But basically they are have the same value, same order, everything, just like they have a different structure. That's why for a list it doesn't really matter, and basically we use for left for performance. It works better. Even if you go to Scala, the definition of for right uses for left, does a reverse and uses for left, and for left is using a while. But it's just all for performance reasons. Formally, that's kind of what happened. But it's a really good question, what happened with the for left and why. When I started reading about this, I said, yeah, but for left doesn't make any sense. So I started, when I did this, I found out that it was really funny. You have another question, right? You got it? It's good? You have a question, right?
I was going to go back to the Stewart question.
Yeah.
That, I mean, my memory of this is that on the left side, the initial algebra, like, the secret of it is that in F map is actually invertible. And so the way that you define fold on the bottom is by inverting that and going around the top. And the F of fold is like this F's map.
Okay. Yeah.
It makes a lot of sense. I mean, probably I'm not going to repeat everything. Probably should give you a microphone. Actually, you should do that. Yeah. You get the mic and do that.
Here, I can just draw it.
Oh yeah. Well, you can use. Oh
Here,
whatever.
anyway, okay. Did not mean to hijack the thing. So my memory of this is just that the initial algebra, like the secret of it is that this is kind of, I mean, if you just like write it out, like you can invert this. And so then like this diagram is the recursive definition of fold, where like fold is go around the other way, and like this is map, and like by going around the other way, you kind of like killed off one layer of that.
True. Yeah. The point is, yeah, you can reverse this, and basically to get this, you travel this, and you get the result. Yeah. Yeah, and this is map. True. Yeah. Excellent. Thank you. I love that, having people that knows more than me. Cool. More questions? Good.
Okay, so the list example and the tree example are different because in the list example you have one recursive call every time you recurse, and in the tree example you have two recursive calls. Is there a library in Scala that can capture both of those in a single abstraction in code, right? So you presented something to understand those things together in our head, but is there a code thing that can express both of those? Is it in CADs or do I need?
I think it's in Matryoshka. I haven't really looked, and I will go in. I had some very small explanation of that, but it was really weird. I mean, I don't totally understand the underlying theory, to the chagrin of my professor. But yeah, that's kind of the trick, the whole trick about that. I'm going to use this again here. Again, it goes back to algebras. It keeps digging into algebras. And basically, you say for list, you have nil or cons that take, there's a list. Cons that takes an element and a list, right? You have for trees, for binary trees, you have a leaf that takes an A and takes, or the branch that takes two trees, right? Let's say, I don't know, another weird data structure you want to add? I don't know, maybe 2 or 3 trees. Well, we can have a leaf with a value, a 2 branch with 2 trees, and another that is a 3 branch that takes 1, 2, and 3. This is going to get weird. let's say this one, let's forget about the names. I look the parameters. This one is something that takes no parameters, and another one that takes value and the list. This one is either of those. This one takes a value or 2 trees. And this one takes either a value, 2 trees, or 3 trees. So basically the elements here are nothing, values, things are recursive, because here we're saying a list is again what we're building, so it's a recursion, a recursive type. Here again we have values and putting together two things. And again here we have value, 2 things and 3 things going together. I don't know, the whole point of saying algebra of types, algebraic data types, is the way you can combine them. And in category theory, alternatives of stuff is called, basically it's a sum. Because basically how it goes with algebra and the definition of how categories go with algebra. But basically, when we have one thing or the other, we call it sum. When we have 2 things put together, we can think this is a kind of a tuple. And in category theory, a tuple is represented by a product. Values, we need something to hold values. And because values are really not, we are kind of focusing on recursive types. Values, we are going to use a kind of a constant to hold them. And a recursion, once that get moved into a category, let's put that this is recursion, but here what we're going to say is, here we're building trees, so if really I'm building trees and here I need trees, basically this is an identity. Because I have a tree and apply a function, I get the tree again, so it's identity. And what else do I need? I think so far I have almost everything. The empty case is represented with 1 because it's just a kind of a generic object, doesn't have any value, doesn't have anything. So that's a kind of very high overview, and I'm just kind of skimming over everything. But basically, with this kind of, I'm creating an algebra to describe any data type. So with this, the list, and if you start seeing things, it will be kind of almost familiar. A list is either nothing or a combination of an element, let's put K, with another list, an identity. Tree is either an element or the combination of 2 trees, 2 identities. And again, this tree will be either a value, or 2 branches, 2 identities, or again 3 identities. So there's a way to describe any kind of recursive data type with this algebra. And that means these are type constructors in our kind of way. So I define a fold for these kind of constructors. So suppose I want to get the sum. I need to define how the sum will work for that, and how the sum will work for that, how it will work for that. And this will be kind of the recursive call. So if you do the pattern matching for the sum, in the case of the nothing, I will return 0. In the case of the constant is often a value. I will just return the value. In the case of the product, I will just return the product is the product of two things. And let's say the left and the right. I will just return the sum of the left of the right. And I'm missing something. In the case of plus, again, I need to do kind of pattern matching. If I have the left side of the plus, I will just return the left side, and if I have the right side, I'll just return the right side. And this one is kind of my generic fold for this. If I have a list, if I apply this, basically your list, list 1, 2, 3, we get translated into we're combining things. Basically, it's a k1 and with a k of 2 with I'm still using tuple, but this is the kind of multiplication. And k of 3. And the last one, that is 1. So using this, we translate that. I have 0. This is a multiplication, a product, so it's with sum. For k, we have, we extract the value, we have 3. And same thing, k2, we have extract the value, we have 2. And again, this one. So basically, and if I can, because I can describe the tree with the same kind of algebraic constructors, I can use exactly the same rules for the tree. So that can be written in code, and that's kind of the basic of recursion schemes. I actually have one experimental library that tries to do this in a weird way. It's not really finished. It works. It doesn't really finish because I have some places that I have to use a cast, because the way I try to write it, Scala type system saying, okay, you're crazy, this is any. I have to tell, no, I know that is an int. But yeah, I mean, that's why I'm not totally happy with that, but it's an interesting experiment. And that's, I don't know, for me this is amazing. It's really weird, convoluted, but on the other hand, you can, basically if you write a macro that looks at the arity of the constructor, you can write this automatically, and you have that translation, your fold will work. Or even without the macro. Suppose you add a new data type, and you basically say, okay, my data type in algebra is described like this, and it will work for default. You don't have to write the code again. Well, that took a while for only one question. Sorry about that.
So is there something in Matryoshka that captures that commonality?
Yeah.
And what's it called? Do you know?
Yeah, but I think you have to, basically, the trick is looking, because I have looked into Matryoshka, and I understand half of that. I'm doing something with this with my professor. I'm trying to basically translate. He has a Haskell code that does this automatically. And I went crazy. I said, oh, let me try to do that in Scala. That's why when I get this any, and I need to really, I discovered that I don't know enough Scala to do that. I'm trying. But he told me, I told him, this library looks similar to what we are doing. And he looked into it and said, yeah, this is what we're doing. The trick is this one. It's a recursive call. Here I put an identity, but it's called fix, because it's the recursion call on types. Look at the fix type, and it will start. This is kind of the basic of Matryoshka. And in the lenses banana, programming with lenses, bananas, envelope, and bar wire, again, it goes kind of not the same thing, but it goes in this direction. That's I don't know if you have a direct translation. I can point you also to my paper that goes through all this.
Thanks.
Thank you. Any more questions, or there got really? Oh, got really weird. Yeah.
One question. So, about the difference between full left and full right in Scala versus Haskell. So, in Haskell, because of laziness, full right and full left are different. And usually, you want to use full right because it looks for infinite lists.
Yeah.
And I guess there's special cases where you want to use full left, but usually full right is the default choice. Scala without laziness, I guess I've heard people say that you want to default to full left. It's more, I guess, exact same.
Yeah.
But aren't they basically equivalent in Scala, where one in terms of the other, because there's no laziness, is there really any difference between full left and full right in Scala?
Yeah, I think the problem with the problem is Haskell with lists is like they're actually lying to you, and they are lists or streams, because there is no infinite list formally. It's either a list or a stream. If you have infinite elements, it's not a list, it's a stream. But yeah, to be safe, because you never know if it is infinite or not, it's safer to use full right, because it always replaces everything. And because of laziness, you don't care if it never finishes. You just take the first 10 elements, and the rest is just a generator somewhere. But yeah, in Scala, because our lists are finite lists, usually if you put performance to one side, they're equivalent. And basically because you can go from a const list to a snug list and go back and forth with just one transformation. So it really is equivalent.
Yeah, so I think one difference that you're saying versus stream is since you apply from the right and start folding over, you can't get to right on a stream, right? So the difference is whether you could get an answer on a
The problem is,
or not.
and that's kind of the tricky part. You never fold on a stream. Let me. Because the stream is a generator. Yeah, 1 second. Let me go back. Actually, a stream is actually an unfold. You start from, you do the opposite. A stream actually is starting from a set of values and generate an infinite stream of values. So, but actually you can fold that. And that's interesting. but it's a little tricky.
You're right, I was confusing an infinite list with a string.
Yeah, but actually, I think the Haskell is kind of you don't care because you can always have the infinite list around and take something. Even if you fold over everything, you take the first 10 elements. That's why if you fold the other way around, if you start from the end and go to the beginning, it will never end. Your fold left will not work. I mean, you get stuck evaluating the list. That reminds me about fold and unfold. Actually, there is ways. The good thing is all these explanations allow you to apply results, and there's kind of things that are called deforestation when you combine either fold and map or fold folds, and that combines into only one fold. It tells you how to go from a combination of folds and fold maps into only one fold without generating all the extra steps. And you have a fold that takes a structure and collapses it. You have an unfold that is the reverse operation that takes a set of values and generates, in case stream, and it generates a lot of elements. And then you have something that's called, if I recall correctly, hylomorphism, because you have the catamorphism, that is the fold, the anamorphism, that is the unfold, and you have something called the hylomorphism, that is a combination of both. And because of function on everything, you have something that from one value expands that, and the fold collapses that. But the fusion of those two allows you to do the operation without generating all the intermediate values. And that's kind of what some optimizations take advantage of that. I think it's, I forgot about that. But there were some examples about that. I think there's one search algorithm, I don't remember if it was quicksort or whatever, that you can see it as like a hylomorphism saying, like you take a list, you generate a search tree of the list, and then you collapse searching of the tree. And because it is a combination of unfold and a fold, you can combine that without basically you do the same without generating the tree. That's kind of how like quicksort or one of those searching algorithm works conceptually. Yeah. Other questions? More questions? Okay, cool. Thank you. Hope you have fun.